Hello everyone, I'm Shantanu Vyas, and I'll be presenting our work on latent embedded graphs for image and shape interpolation. The collaborators for this work are Dr. Chen, Dr. Mohanty, Peng Jiang, and Dr. Krishnamurthy. To begin this presentation, I'll first talk about the motivation behind our work. I will highlight the importance of image and shape interpolation through their applications, the problem that we are trying to solve, and the inspiration in our approach to find solutions to the problem. Image and shape interpolation have been used in a wide variety of applications, from 2D and 3D shape morphing to morphing between faces. It has also been used to generate MRI scans. In recent times, generative neural network models have been widely used for interpolation tasks. Some of the applications include interpolating between video frames, composite shape modeling, synthesizing new designs, and procedural modeling of shapes. In the most general sense, these models learn low-dimensional representation of high-dimensional data and carry out the interpolation task in the lower-dimensional space, which is also known as a latent space. The problem that we identify, however, arises when we look closely at the structure of the latent spaces learned by these generative models, which is typically non-Euclidean. However, in most applications that use these models, linear interpolation has been used to generate new data points in the latent space. We believe that simply using linear interpolation may not always lead to plausible interpolation in the high-dimensional space. For instance, if we linearly interpolate between points A and B in the shown example, we get interpolants that aren't close to the data distribution. However, if we interpolate along the geodesic between these points, we might get interpolants that better respect the data distribution. Prior works also talk about this problem and offer solutions by treating the latent space as a Riemannian manifold, and then offering different ways to compute the geodesic along the manifold. We take inspiration from these works and introduce a simple alternative linear interpolation. First, we learn the latent space of datasets with the help of generative models. Next, we construct a topological structure over the lower dimensional latent space with the help of graphs. Our goal is to have a fully connected structure such that every point in the latent space has a non-empty neighborhood. Some of the questions that we're trying to ask here is, what kind of graphs can be used and what parameters should we set for these graphs to be constructed? We'll answer these later on. Next step in our approach is to approximate the geodesic between 2 points as the shortest path traversed along the edges of the graph. Finally, we resample the path to generate new interpolants. I'll now elaborate on each of these steps in our approach, which includes the methods used for learning the latent space, graph construction techniques, and our interpolation steps. The first step in our approach is to construct and train a generative model to map a data set into a low-dimensional latent space distribution. A requirement for the generative model is that it provides us with a bijective mapping between the original data space and the latent space. In our work, we specifically use different types of autoencoders and primarily different variants of variational autoencoders that are also called VAEs. VAEs typically consist of an encoder that reduces the dimensionality of the input into a latent space distribution that maps somewhat close to a normal distribution, and a decoder that takes sample points from the latent space and reconstructs it into the original input space. Here we show an example of a three-dimensional latent space, which is learned by a VAE for a dataset consisting of rectangles of varying sizes and orientations. Once we have learned the latent space of the dataset, our next task is to construct a neighborhood graph to capture the geometric structure of the encoded dataset. Here, we explore two strategies based on the k-nearest neighbor graph approach, as they're generally known to robustly capture neighborhoods of point distributions. Our first strategy is a k-minimum nearest neighbor graph. The value of k in this method is fixed and is the minimum positive value for which the graph is fully connected. The next strategy is adaptive KNN graphs, where the value of k is selected adaptively in order to remove extraneous connections and long edges between neighbors that aren't directly visible to each other. Here we show a real example of two different strategies. The value of k-min to obtain a fully connected graph in this example is computed to be 3, and therefore each vertex has a minimum of 3 edges originating from it. The adaptive k-min graph, on the other hand, adaptively selects the value of k at each node and results in comparatively lesser number of edges in total, while still capturing the distribution of the data points. The next step in our approach is to carry out the interpolation task. In order to do so, we first find the latent encodings of the data points that we want to interpolate between. Next, We find the points in the latent embedded graph that are closest to the newly encoded points. We then find the shortest path between these points along the edges of the graph. Finally, we perform equidistant resampling of the entire path to find the interpolants. The decoder is then used to reconstruct the interpolants into the original space of the dataset. This concludes our methodology, and now I will talk about the experiments that we conducted and the results we obtained in greater detail. In order to evaluate our method, we performed experiments on 4 different types of datasets. This included a curve-based synthetic dataset, an image-based synthetic dataset, the widely used Fashion-MNIST dataset, and the ShapeNet dataset to see how our approach performed for 3D shapes. For each of these experiments, we compare our interpolation results with those generated from linear interpolation. The generative models that we use mainly depend on the type of dataset that we were working with. These models included the basic autoencoder, convolutional VAEs, and adversarial autoencoders. We talk about the specific model used for each experiment in detail later. Next, we use 2 metrics to evaluate the interpolation results. First, we use the Earth mover's distance, or simply the EMD. The EMD calculates the distance between 2 distributions and is commonly used to compare visual similarities between images and voxels. Next, we developed our own metric called the gradient projection metric, or GPM. So given a pair of images at consecutive time frames, we first compute the pixel-wise gradient vectors for both the images. Next, based on the idea of cosine distance, we compute a weighted cosine distance between the gradient vectors, where the weights are the product of their vector magnitudes. Finally, we compute the root mean square of the weighted cosine distances across all pixels. Our hope is that the metric can detect changes in shapes within images. Here, we note that both metrics are used for image and voxel-based data only. We now move on to the individual experiments and results. Our first experiment was on the curve-based synthetic dataset consisting of superformula shapes. We created this dataset using the parametric superformula equation that can generate a wide variety of shapes by simply changing its parameter values. Our dataset was specifically created by weighting the parameters S, N1, and M. By weighting S results in wider or narrower shapes, weighting N1 results in sharper or rounder shapes, and weighting M changes the number of corners of the shapes. We created our own dataset to better understand and visualize the latent space distribution and the effect that the different parameters might have on the distribution. The model that we used was the basic autoencoder. We wanted to see if our interpolation technique worked well even in non-regularized latent spaces. The latent dimension was set at 3, as only 3 parameters were changed to create the dataset, and also allowed us to visualize the 3D latent space. The key observations we made from the results were that each class of shape having the same number of corners formed individual manifold structures in the latent space. And these were then connected at a seam where the shapes vaguely represented ellipses. This resulted in a multi-manifold structure. Looking at the interpolation results, the linearly interpolated shapes are jittery due to the linear path largely missing the manifold structure. On the other hand, both the graph-based methods showed smoother interpolations from the 4-pointed star to the 6-pointed star, primarily due to traversing the path along the constructed graphs. Here, we notice that the K-mean graph takes a much longer path compared to the adaptive graph method, possibly due to the presence of extra edges. A second experiment was conducted on a dataset similar to the first experiment, with the only change being that the shapes were in the form of images. The generative model that we used here was a convolutional variational autoencoder, which is more suited for image-based datasets. The latent dimension was kept at 3, as only 3 parameters were changed to create this dataset as well. Looking at the examples of results, we see that the intermediate linear interpolations do not preserve the shape and result in missing pixels during the transition. This is likely due to the interpolation path passing through sections of the latent space with missing data points. Both the graph-based methods show smooth and consistent transitions while preserving the shapes with no missing pixels. An interesting thing to note here is that both the graph-based methods produce very similar results, but the K-mean approach took longer paths in both of the experiments. While we currently do not have a theoretical basis for this, we only use the adaptive graph approach for the remaining experiments. The EMD plot for this example shows a sharp peak for the linear interpolation method corresponding to the shapes with missing pixels. For graph-based method, the peaks are seen when the transition is between sharper and rounder shapes. The The GPM plot shows a similar trend compared to the EMD plot. Moving on from datasets that we created, we wanted to test our methods and widely used datasets. For the third experiment, we chose a Fashion-MNIST dataset consisting of grayscale images of fashion products that are categorized into 10 classes. The generator model that we used for this experiment was an adversarial autoencoder that combines aspects of VAEs and GANs. Adversarial autoencoders are good for reconstructing higher quality images compared to vanilla VAEs. The dimension of the latent space is set to 100 owing to the increased complexity of the dataset. The example of the linear interpolation technique shows a quasi-static change between the interpolants before and after the transition from the handbag to the shoe. The transition itself is also quite abrupt. The graph-based approach, on the other hand, shows smooth topological transitions seen by the contraction of the handle of the handbag to the tongue of the shoe. We do not see such a transition for the linear interpolation method. Moving on to the evaluation metrics, the EMD plot for the graph-based approach shows a sharp peak during the topological transition, while the plot for the linear interpolation is comparatively smooth, likely due to the quasi-static nature of the transitions. The GPM plot also shows relatively similar trends across both the interpolation techniques, which show sharper and taller peaks for the graph-based approach. This is again likely due to the consistent transitions between the interpolated images. For our last experiments, we chose a ShapeNet dataset consisting of 3D voxels of a variety of objects. We used only a subset of the dataset, which consisted of 10 furniture-based classes. The generator models that we used for this experiment was a convolutional VAE that works well for voxel-based data. The dimensional latent space was set to 100 owing to the increased complexity of the dataset. In the linear interpolation example, we see that the intermediate shapes lack any perceptual meaning. The shape of the table simply disintegrates into the shape of the sofa, and no other classes of furniture seem to be generated. For the graph-based interpolation, however, we can see that the intermediate shape resembles certain furniture classes that are included in our dataset. For instance, the table initially interpolates to a dresser-like shape, and then to a shape that vaguely resembles a bookshelf, before finally interpolating to the shape of the sofa. Moving on to the metrics, the EMD plot shows sharper peaks for the adaptive graph-based method that correspond to changes in class of shapes. The GPM plot also shows higher peaks for the graph-based method, likely due to the consistent changes in the interpolated 3D shapes. That concludes all of our experiments and results. I'll now sum up the key takeaways, the limitations, and the future direction of our work. In this work, we presented a framework for image and shape interpolation that combined the dimensionality reduction afforded by generator models with graph traversal strategies in order to carry out interpolation tasks. We conducted experiments on a wide variety of datasets to show robustness of our method. Our method generally produced smooth and perceptually consistent interpolations. We showed the ability of our method to interpolate along multi-manifold structures as well. And we also showed an example where our method respects the topological changes between shapes and images. Having shared the key takeaways, I'll now talk about the limitation of our work, which is quantitatively evaluating the interpolation quality. For example, if I were to show these two GIFs of interpolations to a person, they might prefer one over the other. We don't say which one. However, the question arises, what metrics can be used to accurately reflect the visual inspection? Our current metrics did not reflect the results that we showed through the visual inspections. Therefore, there is a need for better metrics that can capture perceptually consistent transitions. With regards to the future of this work, there are several interesting directions that we can explore. Firstly, we can implement different graph construction strategies. Some of the interesting approaches include the rapidly exploring random trees and the space colonization technique. Secondly, the further exploration is required for implementing different generator models, such as GANs, to learn the latent space of datasets. Some models, such as the cluster GANs and infogans, have been able to learn and modify the latent spaces to improve data interpolation. Lastly, we need further research in capturing topological shifts for interpolated shapes. One way to study this further is to create datasets that specifically characterize these shifts. That concludes the presentation. For more details about our work, please read our paper published in the CAD journal. As a special mention, I would like to thank the NSF for funding my talent award. And now I can take any questions. Thank you.